So I think I need to spend some time explaining what are these oriented matroids, and I'll also tell you where I lied. So these are oriented matroids. I actually mean rank 3 oriented matroids. Okay. So anyone who was wishing for something higher dimension than rank 3, I'm sorry to disappoint you. Okay, but I'll try to explain to you what rank 3. Already oriented matroids are getting interesting in rank 3. Okay, so I'll spend some time explaining what this is, and this is some ongoing work. So this is ongoing work with Alfredo Hubbard, who is in New York. And it's based on some questions of his, and I made some ridiculously simple observation this summer that suddenly started the snowball rolling. Okay, and now I'll show you what this simple observation is. It's related to these convex representations. But I need to explain to you what are oriented matroids. So there are several names. Some people call these order types or abstract order types. Okay. So I'll start by explaining what these are. So consider now you have a set of points, finite set of points in the plane. Here. This is in the real two-dimensional plane. Okay? Now what does an order type or an oriented matroid, what are we supposed to capture? Well, I want to capture some combinatorial information, and what I want to capture is basically the convexity properties. That's one way of saying this. Let me add another point here. Okay, so what do I do? What is this information I want to record? And why do I want to record this? Well, it turns out there are many problems that start like this. Take n points in the plane. And then you have some beautiful theorem about these. All right? And seemingly they could even involve some distances of some enclosing curves or something like this. But there are many of these problems. It turns out it doesn't really matter what the distance is. It's the metric of R2 is not playing a role at all. What's playing a role is the convexity properties of this point set. And that's what this order type is supposed to extract. And then one abstracts this and gets abstract order types, which are these oriented matroids. So that's, first I explain to you what this is. Okay. So if I have this point set, let me label the points in addition. P1, P2, P3, and so on up to Pn. Okay? Now if I wanted, I could now record this in a matrix. Well, these are real numbers, right? x1, y1 are the coordinates of this one, and so on. And let me just add a row of 1s at the bottom. Okay? So this is a matrix like this. Keep in mind that there's a row of 1s on the bottom. Okay? And now let me tell you how to find the order type now. Okay? Now the order type is going to depend on the labeling, or the way I define this, it's going to depend on the labeling, but then we mod that out afterwards. Okay, so now let me define another function. I, j, k, these will be integers. Between 1 and n. Okay, so these are just going to represent my columns, and this is going to be the sign of the determinant this determinant. Okay? So I just record the signs. That's, I call this the chirotope, or order type, of this point set. Okay? And so I said I'm not going to go above rank 3, but now you can maybe already imagine how to do higher dimensions if you wanted. Okay? This would be maybe an RD by n matrix, right? If you wanted to do this in higher dimensions. But we'll restrict ourselves to the plane because that's where things already get interesting.
Then you also increase the number of points or number of Convex is IJK.
Right, so then, I mean, you'll always be looking at these d by d determinants. Yeah. Okay, so now I can think of this map, chi, as a map going from triples of indices to -1, 0, 1, right? That's what this chi is. So that's my chirotope, or my order type of this point set. Okay, recording the information about this point set. Now, what does this point set? Now, what does this map record? Can anyone see that offhand? Well, it's very simple. It measures if they're on a line. Yeah. How does it measure that? It gets mapped to 0. And if it gets mapped to 1, what does it tell me? Well, it tells me basically, let me call this one I now. Here's Pj. Look at this line ordered from, look at the directed line going from I through j this way, yeah? If it's +1, where do I know pk is? It's on this side, right? And if it's minus, it's on this side. And that's what this order type is telling me. Simply, it's telling me whether the triangle, if they lie on a line, or if they turn this way or the other way. Yeah? So it simply tells me the orientation of each triangle. And that's what I call the convexity properties of this. So it turns out this is all one needs. And I would say that 2 points have the same order type if you can label them in such a way that you get the same chirotope. Right? This is a natural way to define 2 combinatorially equivalent point sets. Yeah? Okay. So that's one way of getting an oriented matroid. Now let me write in general what this is. So in general, we'll look at maps just like the one I said, -1, 0, +1. So this will be an oriented matroid on n elements, a rank 3 oriented matroid. And basically it should satisfy whatever I see here. Now this chi should be an alternating function since it involves a determinant here, right? So it should be an alternating function and satisfying the Grossman-Plucker relations. And now I'm going to make a guess and put 2 dots here maybe. Relations. Okay. I'm not going to say what those Grossman-Plucker relations are, but that's just some combinatorial relations. Okay? Now these guys, they're equivalent to the following. And here you need to make the proper modification if you want to go to higher rank. Let's see, this is for every subset of n, where the size is at most 5. The induced map this is not the 3-sphere, this set tripled to corresponds to a real matrix. This is something called the local realizability theorem. Okay? So this map, an alternating function from like this, satisfying the Grossman-Plucker relations, that's the same as saying that whenever you take 5 or less columns, you can actually find a real matrix that does exactly what that map says. Right? So this is called local realizability. So if you have local realizability, then that's the same as satisfying these Grossman-Plucker relations, and you have an oriented matrix. Yeah?
So does that generalize to higher dimension you change?
Yes, so in general, here should probably be d plus 2, I'm guessing. Yeah? 2d minus 1? No, I think it's d plus 2. Yeah. It could be 2d minus 1, but I think it is d plus 1 actually. D plus 2, sorry. Okay, so all of these things can be found, well, basically date back to something called Lorentz, Falkland-Lorentz, who were two of the sort of founders of oriented matroids. 1978. I'm going to mention their theorem as well, which is particularly nice for these rank 3 oriented matroids. So now I would like to visualize what are these rank 3 oriented matroids. So I know some of them I can get like this. Turns out all of them you can get almost like this by point sets. Okay? And you get them as follows. You draw a bunch of points, n points, and you connect them by lines, except that the lines may not necessarily be straight. All right? So for every pair of points, there should be a unique curve which goes off to infinity in both ends, so a simple curve passing through every pair of points. Every pair of curves should cross in exactly one point, and there they should cross transversely. All right? So for example, this one should cross maybe here. Okay? See, when I put in these curves, then I can read off the matroid in the same way as here. Right? So if I have this plus-minus relation, right, it tells me I place 2 points, call this I, call this J, then I draw the curve, right? I have a directed curve, and now I know from my matroid that K should lie on this side. Right? I know that K, another index should lie on this side. And then I keep connecting and keep connecting. And that's how you can make a geometric representation of any such rank 3 oriented matroid. Okay. Now this collection of curves is called a pseudo-line arrangement. And these have been studied since Levy. I think this is the first place the word pseudo-line arrangement showed up, by Levy in 1926. And they were later studied by Grunbaum and by Goodman-Pollock, and then by many, many people. Yeah? So that's some of the history. Let's see. This is 1970s. This was taken up. He wrote some monograph about these, and 1980s. Goodman and Pollock did a lot of stuff on these things. And now a lot of people have done things about pseudo-line arrangements. These are quite common object now.
So any such function can be represented?
Yeah, this is, yes, right. So the Falkland-Lorentz representation theorem is that any such function has a representation like this. Yeah? This is called the Falkland-Lorentz representation theorem. And the representation theorem goes to higher rank matroids as well. So instead of lines, these should be what they call pseudo-hyperplanes. So you make something called a pseudo-hyperplane arrangement. Yeah? Okay. Any questions so far? There are, of course, many other ways I could represent this. I could represent this as a 3 uniform hypergraphs. That's another way. One could think of these things. Sometimes a simple arrangement, so such an oriented matroid is called simple. That means that this map does not include 0. Okay? So these are simple oriented matroids. Means you don't have 3 guys on the same line. Yeah? And you can easily represent this as a 3 uniform hypergraph. That's another way people view these things. Right? By just, for example, recording the plus ones, if you want. And you need to encode how many these Grossman-Plucker relations in there. That's easy enough. That's easy enough. Okay, so number of these rank 3s, that's an important question that people have asked themselves. So if you encode these as these guys, you get some obvious upper bound, something like this, right? That's obvious. But the true upper bound is something like this, constant and squared. So about this many different such functions, all right? Is it clear what different means? Yeah, I explained that here, right? So up to relabeling, you make the same, you make the same function. And what's important is the realizable ones. So there's some interest about the realizable ones. Those are the ones that actually come from real matrices. That's called the realizable oriented matroid. Yeah? So one might want to compare this number to the number of realizable oriented matroids. And this is a different constant, C prime, and log n, approximately. And another reason that these things are of interest and people want to count these is that there's some direct relation between these things and convex polytopes, and counting how many different combinatorial types of convex polytopes there are. Okay, so this lower bound was constructed about the 80s. Sorry. This is matching C, let me call 1, and log n, and here. Like this. Yeah? These are matching bounds. So asymptotically, this is maybe the right answer. Okay? So lower bounds are usually by some kind of constructions, right? Upper bound, this is an interesting upper bound, comes from some real algebraic geometry. Okay, so once you look at this guy, it's enough to consider only simple oriented matroids, and you look at this guy, you see that what determines this matroid are these determinant functions, right? So you can encode this whole thing, the space of all oriented matroids, as some semi-algebraic set, and then there's a theorem by Milner about the Betti numbers of this semi-algebraic set, depending on the degrees of defining things, and that gives you, with some hand-waving, gives you these bounds, right?
Milner-Tom.
Milner-Tom, right. So this follows from Milner-Tom theorem, right? And well, this upper bound is some combinatorial counting argument. Yeah? I want to give you an example because we will use it later. I want to give you an example here. I'll show you that there are very many oriented matroids. So it's interesting to have this one and compare it to this one, because then you can really understand that if you draw some random arrangement. So if I drew 100 points in the plane, I started connecting these lines, right? You might ask, is this going to be a realizable arrangement? And most likely not, right? That's what those bounds tell me. And in fact, when I draw, even if I'm using a ruler, my lines aren't really straight lines, and maybe even when I try to draw with straight lines, I'm probably not drawing really a straight, realizable oriented matroid, because they are actually very rare, right? So let me show you how to make many oriented matroids. I start like this, take k points, on the grid, move here and take another k points, just a translation. Make another translation exactly at the middle and add the midpoints as well. Okay? Now I'm going to get a bunch of collinear triples. And so on, yes? And like this. And I do this everywhere. I get a bunch of collinear triples here. Now what am I going to do? For each guy here, so some guy near the center, well, there's going to be all of these are going to be center chords of triples passing through, right? So what I do now locally around this guy is I saw some line going through. Now I'm going to choose, should I tip it a little bit over or should I tip it a little bit under, right? So maybe I let it go a little bit under like this. And some chord that came here, well, let me tip it a little bit over. Yeah? And you have all these choices of these roughly half set of the points. Here you can make a choice for each of these triples. Which way should I flip it? Now when you do the count, you'll get something here. Like maybe a constant 1/9 or something like this. I don't know. You can do the count. So there's a simple example illustrating that you can actually generate very many of these oriented matroids. I thought I would mention, since this is from this year, somebody made improvement on this one. The constant is approximately 0.6571. And
That's exact?
no, that's an upper bound. Lower bound here, 0.188. Yeah. Okay. Yes. So now let me describe you something else that happens in this kind of game where we play with endpoints in the plane. So that's going from collections of points to collections of convex sets. So points are just very basic convex sets. So instead of taking a family of points, I might think of a collection of convex sets, like this. Yeah? So that's basically, something that we do for many, many problems in combinatorial geometry that start with take endpoints in the plane or in space or something. Then you ask the similar, you try to modify the question for take a collection of convex sets, yeah? And see how things change. So now this is, a while ago, Alfredo looked at these oriented matroids, looked at these order types, and he said, let me replace by convex sets, okay? So let me draw here. When I'm thinking of oriented matroids, every 2 points should be distinct, okay? So 2 distinct points here. Now what should it be in the convex set case? Well, 1 point becomes 1 set. What should the next point be? Should also be a set. You might think they should be disjoint, but it turns out that's not really necessary. They could be like this. So what's important is that these 2 points, I and j, they have this common line, and there is a half space that supports them, which points up, and a half space that supports them and points down. And you want the same thing here. There's some supporting half space this way, and some supporting half space this way, right? So for us now, this is how we will go from a pair of points to a pair of convex sets. They could be disjoint or they could be overlapping. What we don't want is something like this. This is the picture that is bad for us, because here the supporting planes start getting many, and you can easily make a polygon going around like this and getting as many supporting planes as you want, right? So we want these 2 supporting planes to become just 2 supporting planes. What about a collinear triple? What should that go to? Well, when I look at these, I see there are 2 outer ones, and their convex hull contains this one, right? So in my model, it could look like this. Convex hull, each pair of these is of this type, and the convex hull of 2 of them contains the third one. Yeah? That to me is a collinear triple. And what about this proper triple forming a triangle? Well, that should go over to these guys, and when I take their convex hull and I walk around the convex hull, I should meet their boundary. I should meet each set exactly once. So is this exhaustive? Is this all the cases, or can anyone see anything else that could happen? Remember, this is my basic assumption. Every pair looks like this, right? Well, there's one thing that could happen. I could have a set here and a set here and another set here. So 3 convex sets could form, in a sense, a quadrilateral. All right? There is no analog of this. We have no analog of this for points. Okay? So we call this type 0, type 1, and type 2. Okay? So as long as I assume this part, you can easily check, every triple is going to look like one of these. Yeah? And now what Alfredo observed was that if you put a bunch of, so you take a family of convex sets, so this is n convex sets, and suppose they're all type 0 or 1, then this gives me an oriented matroid. Okay? Now I read off the oriented matroid in the same way. For points, I would map this triple to 0, and I would map this triple I, j, k, while I would orient it positively if they turned this way, right? And similarly here, I, j, k, well, I can read off an orientation. I don't want to include these guys because I can't really decide what is the orientation of this triple, right? So as long as I exclude these, then I'm okay, and I put convex sets in the plane like this, I will get an oriented matroid, just in the same way as I got an oriented matroid from points. Yeah? So this will be the set of oriented matroids, the realizable ones, the ones I can get from points. This will be the ones I can get from convex sets. And let this just be the set of all oriented matroids. So his observation was basically that you have this inclusion, right? Because why the oriented matroids I can get from convex sets, clearly they include these, right? Because points are convex sets, right? And everything here is oriented matroids. Now this inequality, this inclusion, this is strict. Is this obvious? So this class is bigger than this one, right? So I made an example of this around 2006, and Poch made also an example around the same time, showing that this inequality was strict, or this inclusion, right? There are matroids here that you can get from convex sets that are not realizable ones. And then our new observation, well, it's in the title, right? That was inequality, all right? So in fact, any oriented matroid one should think of in this way. Well, one can. And now comes the part where I'm going to try to convince you that you should think of them in this way. All right?
So you're excluding type 2?
Yes. Type 2, we'll get back to the type 2s later. But for an oriented matroid, I want an orientation for each triple, right? That's why I don't want to include this type 2. Because I can't tell if the triple ijk in this case is going counterclockwise or clockwise, right? Okay. So now I claim that every oriented matroid can be drawn as a system of convex sets. That's what I want to show you now. And so far, the people that we showed it to were so surprised over how simple and straightforward this was. I doubt you guys will be as surprised because you guys haven't thought about this, and maybe for some of you, this is the first time you see oriented matroids, so you don't know what to be surprised about or not, right? Yeah. Okay. So now I have to go back a little bit to about 1980, where Goodman invented something called the allowable sequences. This is related to combinatorics of point sets. So I'm going to try to make a drawing. Let's see. Let me label these points 1, 2, 3, 4. Okay? Now the allowable sequence was his way. I guess he didn't know much about oriented matrix at the time. And he also was interested in point sets in the plane, and he said, I want to encode the combinatorics. There's a problem about point sets he wanted to study. He wants to encode the combinatorics. Clearly, that doesn't depend on any metric properties. So he did maybe the most natural thing. He took a line, a directed line. He projected the points down to this line, and he read off their order. This was a directed line, right? 1, 2, 3, 4. Now the thing he did was he rotated the line, okay? And he saw what's happening when I rotate this line. Can you see what's going to happen? So as I rotate, change this direction continuously, I will reach, this will be the direction I reach orthogonally, right? So what happens? These two are going to swap positions. So when I'm slightly past this orthogonal direction, I'm going to see the permutation 1, 2, 4, 3, right? And then he keeps rotating. And this will be a combinatorial sequence of permutations. Or sequence of permutations, he called this an allowable sequence. So in this case, I'm going to write this up. 1, 4, 2, 3, 4, 1. Now why don't I need to keep writing here? I didn't go all the way around. I went around to this position, right? 4, 3, 2, 1. I went 180 degrees, right? Or that was a rotation by pi. Okay? So from here on, the sequence is just going to repeat itself, but in the opposite order. Yeah? And then I'm eventually going to get back to 1, 2, 3, 4, and it's going to repeat itself. So it's an infinite sequence, right? Periodic sequence. So this, of course, very naive, and this, they invented these allowable sequences, and I think they dated this back to, I have here, someone described precisely this sequence in 1881, saying that take any sequence of points, you can get this permutation sequence, and what this person mistakenly said was, and clearly take any such sequence, you can get a collection of points. Now this is not true, all right? Because it turns out that this sequence contains precisely the oriented matroid. Contains a little bit more. But it contains in particular the information about the oriented matroid. And for any oriented matroid, I could get this. All right? And there will clearly be sequences like this that cannot come from straight line point sets. Right? Or straight point line configurations. But what Goodman also did was he looked at this sequence and he said, this is pretty nice, let me write this down in a different way. 1, 2, 3, 4. Now what happens in this sequence? So in one half period, each index swaps place with each other index exactly once. Right? So let me look this one. This goes straight, straight. So straight, straight. Something like this. Yeah? What is 2 doing? It goes like this. It's too complicated for me to draw this down now, I see. Like this. Like this. Okay, so now I'm just recording the position of 1. I tilted it like this. Yeah? Now what does this look like? Well, this looks exactly like what I call the pseudo line configuration. Right? I have a bunch of curves going off to infinity, each pair crossing exactly once. Right? This he called the wiring diagram. And the bound I told you about, this upper bound here, And basically any known upper bound of this quantity dates back to analyzing some combinatorial counting of these wiring diagrams. Right? So the first exact bound was done by Knut, but Richard Stanley had a formula for these guys, which is pretty nice, so I'll mention this. So Stanley counted that, here's what he counted. I'll write the formula. Oops. This was his exact formula for the number of ways to start with the permutation 1 to n, and then you're allowed to swap each pair. You're supposed to swap each pair once and end at the opposite permutation. All right? So Stanley counted how many ways can you do that, and he got this number. Right? Now this isn't exactly the oriented matroids or the allowable sequences we want to count. Can you see why? Well, in this picture it's not very clear. So the reason is, consider a point configuration like this. Okay, and I want to get this allowable sequence. I could make them cross on this side, or I could make these two parallel lines, or I could make them cross on this side. That will change where they are in this sequence. All right? So when I write down this sequence, whether this crossing happens on this side or on this side is going to change the position of, it will interchange two adjacent things here. Okay? So in the sequence it will look like this. I have something ij and later kl. Next term is going to be ji, kl, and the next term is going to be lk. Okay? That's if they cross on this side. Or I could make this KL swap happen before the IJ swap. That corresponds to crossing on the other side. All right? And for us, for oriented matroids, this is exactly the same, but Stanley counts these as different events. So these are different sequences. So he's not counting exactly the same thing, and if you factor out relabelings and everything, you get within a log factor something of the right result here. Is that clear? So anyway, that's nevertheless a very impressive formula. Does anyone know this number? So the story behind how he arrived at this number was Goodman and Pollack started writing down these sequences. They started plugging them into a computer. They computed how many ways to, they started with 4, 5, 6, 7. They gave a seminar talk similar to this. They presented, yeah, we did on a computer, we have the numbers for 4, 5, and 6. And some guy was in the audience who was a combinatorialist. He went to Stanley and said, you know what numbers they found? He told them the first 3 numbers. A week later, they got a letter from Stanley saying, is this the number you're looking for? And he recognized those first terms, and so Pollack told me that it took them a few days to just check that asymptotically this was within the range they were looking for. And they started believing it, and it turns out that this was the right number. Right? Later, Edelman and Green found a nice bijective proof of this one. So there's some bijective proof to some standard Young tableau of perfect staircase shape. Yeah. So, okay. So now the solution is very close, these convex representations. Let me erase here. Okay, so once I give you the convex representation, then I'm going to do a little babbling that is not so... I'll show you some things what this is related to. Okay, so I have now the oriented matroid. I can use my Falkland-Lorentz representation theorem to put these as points in the plane and draw the curves. Yeah? And once I have these curves, I can read out this allowable sequence. So from my oriented matroid, I can get my allowable sequence. Yeah? pseudo point configuration. And from my allowable sequence, I can write down my wiring diagram. That's precisely what I have here, right? So now let me I'm going to cut the plane at the origin into 2 and choose 2 equal regions. Yeah? Okay? So in this case, I'm going to do this one here now. So n equals 4, so that should be 4 choose 2, 6, 12 regions. So I have cut into 12 equal regions now, right? Now let me write down here 1, 2, 3, 4. Yes? Here, what should I write down? 1, 2, 4, 3. 1, 2, 4, 3. By the way, so this is our observation, the one we made it this summer. Can anyone guess what I should write here? 1, 4, 2, 3. Right? 4, 1, 2, 3. I'll just put the numbers. 4, 2, 1, 3. 4, 2, 3, 1. 4, 3, 2, 1. Yeah? Now I connect the dots. Well, I look at 1, and I take the convex hull of those points. Okay, now I continue that this was a cyclic sequence, so it continues like this. Yeah? 2 here, and well, I need to think where this comes out. It will come out somewhere. Yeah? And I keep doing this. And what am I getting? I'm getting convex sets, right? So let me do one last one. 3. 3, 3. I'm a little afraid I'm going to mess this up. Let me try. That looks right. So here was where I needed the colors. Let me keep this one named white. The white one, white convex set, that's 1. The red convex set, that's number 2. And the yellow convex set is 3. Okay, and I could draw the 4th one, or if I had more points, the 5th one and 6th one and so on. Yeah? Well, this is enough to illustrate my point. What is the order of 1, 2, and 3 here? If I go in the order 1, 2, 3, I'm walking counterclockwise. Here's 1 on the boundary, 2 is on the boundary, and 3 is on the boundary. Right? Same order. So 1, 2, and 3. Yeah? So the orientation is preserved. So do this for any wiring diagram. Draw the circular wiring diagram. The circular wiring diagram is a representation by type 1s, type 0s. Yeah? What would a type 0 look like? Well, it corresponds to, in the wiring diagram, it corresponds to 3 guys crossing simultaneously like this. Yeah? So that would mean instead of this red guy sticking out here, he would actually come here. Okay? So if it was a type 0, this red guy would go through here and would never appear on the convex hull of that triple. Right? He would be on the inside. So there is the representation. Now maybe things don't look completely convex, but you just take these guys approaching very close to each other on each one. Yeah? And you get precisely something as you let the limit of let the distance here, let that limit tend to 0. These things will start looking almost like 2n gons, where n is n choose 2. Yeah? That's what these things look like. So every oriented matroid has a representation by 2n gone. 2 capital N. Okay, so now I'm going to babble a little bit on. I don't have much more time. Okay, so then I have many things I wanted to say. I want some enumerative formula, like Stanley's, for these diagrams. That's one thing that we would like. All right? I can include type 2 into these diagrams. Okay? So I can draw type 2, type 1, and type 0. All of this I can fit into the same type of circular diagram. I get a different kind of sequences, not exactly the allowable ones. And what I want is Stanley's formula for diagrams including type 0, type 1, and type 2. All right? I want this enumerative formula. That would be nice. Here's another theorem that we have. Here's a simple observation. This number, 2n. In fact, after I drew this, I can make reductions and I can get that each convex set in my representation of this matroid can be done with n minus 1 gons, or basically n gons, where little n, not big N. Right? That saves a bit on the complexity. Right, so now it's time to introduce some complexity measure on the oriented matroid. How many vertices do I need per convex set to represent that matroid? So the realizable ones, right, so point configurations. Well, these are, in our convex representation, that's just 1 gons. You can think of that, right? Now there are oriented matroids that can be represented by 2 gons, and so on, and so on. Every oriented matroid can be realized by n minus 1 gons. Okay, each set is an n minus 1 convex polygon. Yeah? Now I'm going to go all the way up to n squared, roughly n squared gons, since that's what I had here. Now you notice this circular diagram, that's very canonical. So now we have another theorem. Take any representation of an oriented matroid. All right? It's going to happen within this range. Now if I allow the point sets for each individual polygon to become up to n squared gon, I have the following theorem that, in a sense, I can continuously take this one, transform it into any other one. Okay, so here was an oriented matroid given by convex sets. Here was another oriented matroid given by, here was the same oriented matroid given by a different system of convex sets. If I allow the number of vertices to go up to n squared, I can continuously move these things, and transform this one into this one. Okay, working within the space of n squared gons. Does that make any sense?
Where are the n squared gons? Where are they?
In the plane. No.
Compared to these convex sets?
These are the n squared gons.
Okay.
N was so large that it actually looked like some curve, but yeah. Okay? So let me just say it like this. Take any representation by convex sets. Okay? I can speak of families of convex sets of being close in the Hausdorff distance. Yeah? Now, given 2 representations of the same oriented matroid by convex sets, you can continuously deform one into the other. All right? And here I'll use Hausdorff distance to say what is continuously, such that on the whole path along the way, they have the same oriented matroid. All right? And in fact, I can do this working within the space of n squared gons. I never need my things could be polygons, and they never need to exceed n squared vertices. Yeah? Now this also may not seem to have, so what, right? The thing is, take 2 point configurations, so 1 gon representations of some oriented matroid, right? Take an oriented matroid represented here, and the same oriented matroid represented by another point set, but the same oriented matroid. This was a famous old conjecture called the Isotropy Conjecture. Said that this one, if those 2 have the same combinatorial type, the same oriented matroid, there is a way to continuously deform this one into this one, such that along the way I always have the same oriented matroid. Yeah? This was a famous conjecture from maybe the 50s. And until the 80s, this was widely believed to be, this must be true. And then a guy named Nioff, he turned this upside down and he said, not only is this not true, this is as false as you could imagine it to be. All right? So for this, you need to define something called the realization space. So given a given oriented matroid, which is realizable, like I said, you can write it up as this real 3 by n matrix, right? You can look at the whole space of 3 by n matrices which realize that given abstract oriented matroid. Yeah? And like I said, this is going to be some semi-algebraic set. All right? Now basically what Nioff showed was that take any semi-algebraic set you want, he'll construct a point set whose realization space is that semi-algebraic set, up to some small modulo something called stable equivalence. Okay, but something that does not change the homotopy type of the set. So in particular, you can have point sets whose realization space is as many connected components as you want. You can have whatever Betty numbers you want. Right? And this can happen here. And now we know that we shouldn't think of oriented matroids as single points for each element. We should think of them as convex polygons. Yeah? And if you can allow the polygons to have this many, well then suddenly the whole thing, well, not only is connected, we show that it's a contractible set. Okay? So the realizations within n squaregons is a contractible set. Right? If you cut off here, it's not contractible at all, it's disconnected. It is whatever topological set you want it to be. You'll find some point set that has this as realization space. And here's a whole range of things that we are exploring what should happen in between. But I think I'm close to the end now. There were some other problems I wanted to mention, but this one and this would be nice to understand how to do, if Stanley's formula, if there's some relationship, these diagrams to something else. Yeah. Okay, so I'll finish there.